So welcome to Module 6. You made it to the last week of new material. Yay! So exciting. You're almost done with the class. Woo woo! If you made it to Module 6, you're almost done with the class. A couple things to talk about. This week there's only going to be one Module 6 live lecture since it's a little bit less material to talk about. Tomorrow's live lecture is going to be a few more examples just in case anybody needs it, and then we'll talk about Deliverable 7 tomorrow. So today we're just going to talk about Deliverable 6 and kind of concentrate on that one. Now, this week we're going to talk about correlation and talk about creating regression equations. So we're still going to be talking about this idea of two variables. And we're going to talk about the relationship between them, such as like, does one variable cause the other one? In your notes, I use the example, or in the course announcements, I use the example of smoking and cancer. And we've found out there's a connection between the two, right? The more you smoke, the more likely you are to get lung cancer, unfortunately. But those are two variables that are connected. So we would say they have a correlation. But we're going to talk about other things. So just throwing this out there to start. If you want to win a Nobel Prize, should you study subjects like physics, chemistry, and economics, or should you just eat more chocolate? Now, if you're a normal, everyday person, you're probably going to assume I should probably study those subjects, right? Rather than eat chocolate. Me eating chocolate doesn't mean I'm going to get a Nobel Prize. But what they did is they wanted to study these two subjects. So they made basically two sets of data and then they're comparing the two. So is there a relationship? And does the increase in one variable increase or decrease the other variable? Is there a relationship there? That's really what we're looking for. So here's this study on chocolate consumption, kilograms per capita, and the numbers of Nobel laureates per 10 million people for each 23 different countries. So here's the data they collected. They said, okay, so here's how much chocolate is consumed, kilograms per capita, and then here's how many Nobel laureates or winners of Nobel Prizes there were in each of these countries. So each row is a different country, and they're just comparing the amount of chocolate consumed and how many Nobel laureates there were. There doesn't seem like there should be a relationship there, right? You're like, I don't think eating chocolate is going to make a difference. But they want to look, if a country increases chocolate consumption, is it likely to experience an increase in the rate of Nobel laureates as well? Well, if we were to graph the data in what we call a scatter plot, notice that most of the data is pretty close and it kind of goes along a line, kind of looks like this, kind of in an upward fashion, meaning that as chocolate consumption increases, it looks like Nobel laureates increase as well. So can we draw that conclusion? Well, that's what we're going to study today. We're going to get into the nitty-gritty and look at, can we make a conclusion that these two are correlated somehow? And I'll talk about the difference between correlation and causation in a little bit so we know the difference between the two. So recall last week we talked about making inferences or conclusions about the data. We talked about hypothesis testing. Well, we're still going to continue that, but our hypothesis test this week is going to be a little bit different. It's going to be whether or not our data has a linear relationship, and we'll talk about more what that means. So we're going to talk about if these two variables have a correlation, and we're going to do that by looking at linear correlations and identifying their equation of the straight line. So this might feel like a little bit of algebra. Do you guys remember algebra, doing linear equations, perhaps graphing them or anything like that? Does that sound familiar? We're gonna pull a little bit, but it's not going to be too much, I promise. You know Excel does most of the work for you. So Lori's super excited there, I can tell. Okay. I love your guys' responses. They always crack me up. So let's start with something a little bit easy. So we're going to talk about how to create a scatter plot in Excel. This is a fun part. If you have the data, scatter plots are really easy to do. All you have is 2 columns of information and they're related somehow. And you just select both columns and you're going to create a scatter plot which plots all the data as points on your grid. And each axis will represent a different variable. So here is a scatter plot that represents the average daily temperature and the number of visitors. And as you might assume, as the temperature increases, gets larger, moves to the right, what happens with our data points? They get higher, right? Meaning that the visitors increase. So what we see here is that it looks like it's going along this linear line where as daily temperature increases, the number of visitors increase as well. Now, before we move on, I just want to show you real quick how to do that in Excel. So I did give you a download Excel sheet to practice on. So you can download that and look through it a little bit. But this is the first sheet here, and you see 2 different pieces of information. You see temperature and then ice cream sales. And as you can assume, as the temperature increases, the ice cream sales also increase. Just a heads up, this is degrees Celsius. This would not make sense as degrees Fahrenheit, would it? 25 degrees Fahrenheit, I'm not buying ice cream. But Celsius, yeah, okay, I'll do that. So just go ahead and click and drag and highlight both columns. Then you're going to go to Insert. So up here to Insert. Boop. Then over here in Charts, there's going to be a scatter graph right there. You're just going to click on that and then choose the first option, which is scatter. And if you click on it, you'll see that it comes up with your scatter plot. You can edit this by clicking on different ways. You can make it look, okay, maybe we like it in black. It looks cool, right? Okay. You can also change it, do quick layout and change whether it has different information on it. You can add axis titles if you want to change that. Remember, you can double click on these and change the title of the graph. There's lots of stuff you can do here. Play around with it a little bit so that the graph actually represents what you're trying to say. So down here you can see the temperatures and this is the sales. And they're all as dollar amounts. Okay, so you can kind of see there looks to be like a linear equation that could represent that line. So, is everybody kind of familiar with scatter plots? Have you guys used scatter plots before? Or at least used that insert graph? Yeah, so hopefully it's not too intimidating. Just select your information and press that scatter plot. That's all you're looking to do right there. Now let's go ahead and talk about correlation a little bit. And that's the relationship between the 2 variables. A correlation exists between 2 variables when the values of one variable are somehow associated with the variables of the other. In other words, if one variable increases, the other should increase as well. Same thing vice versa. If a variable is decreasing, maybe the other variable decreases as well. Okay, so you're either going up or you're going down, but there's some type of relationship there where the changing of one variable is changing the other variable. Essentially, that's what's happening. That would be a correlation. A linear correlation exists between 2 variables when there is a correlation and the plotted points of paired data result in a pattern that can be approximated by a straight line. So today what we're going to do is we're going to take that data and we're going to try to come up with that equation of the line. That line that I drew, that straight line, we're going to try to come up with the equation that represents it. Now keep in mind that that line is an approximation of the data. It doesn't fit the line, the points exactly, but it's an approximation. So here we have an example of a scatter plot where there's a strong linear relationship. And what that means is that all of the points are very close to creating a straight line. I think you would all agree this kind of looks like a straight line. Hence, it's a very strong linear relationship. It's almost like they're lining up for us. Okay. Now, to determine if there is a correlation between two sets of data, is there a correlation? Do we know? We have to come up with R. And R is a new variable we haven't talked about before. R is called the linear correlation coefficient. Now that is a mouthful, right? You're sitting there like, say that again. Linear correlation coefficient. So R is going to be the guy that tells us how close our data is to a straight line. He's going to tell us that. You may be like, how does he tell us that? Well, before we get to that, let's talk about exactly what R means. R is the linear correlation coefficient for sample data. So when we're looking at sample data, we're going to use R. But we've learned in the past, when there's a variable that represents sample, there's also a variable that represents population, right? Well, here we're going to introduce a new Greek letter as well. It's called rho. It's pronounced as rho. It kind of looks like a P, but it's not a P. It's really a Greek letter. So just know that this P here, rho, is the linear correlation coefficient for a population, whereas R is the same thing but for a sample. That's the difference between the two. So here's a little chart that's going to have different R values. So what I want you to look at is, first one, let's start with the leftmost value. So this R value is a 1. 1 is the largest value you can have. You're going to have an R value somewhere between 1 and negative 1. Okay, that's as far as you can go. If you get an R value that's 1, that means you've got a perfectly straight positive line. Boom! Look at how that data fits and just creates this amazing straight line. Oh, wow. Look at how perfect that is. That's going to be an R of 1. Okay? This is going to be an R of 1. It's supposed to say equals. Let's just reset. Okay. Now, as you start to move towards 0, notice what happens. So here's 1. Here's 0.8. Notice some of the points get a little bit off of that straight line. It's pretty close to a linear equation, but it's starting to get a little bit off. And then notice as we get closer to 0, what happens? The lines start going away from that straight line, right? They start migrating away. So it doesn't fit that line as well. And as you get to 0, 0 means that there's no correlation. 0 means there's no correlation going on here. There's no relationship between these two variables. And then notice as we start to get more negative, closer to negative 1, what ends up happening is you do have a straight line. However, it's a negative straight line, meaning that it's going down instead of going up. So it's a negative correlation. So the idea is 1 and negative 1 are amazing. They're linear correlations. They have a great relationship. Woohoo! But as you start to get to that 0, so closer and closer to 0, you're going to find that there's less and less of a correlation between those two variables. So that's what it means when you get that R variable. So if you had like an R of 0.5, it'd be over somewhere in between here. So it would be in the middle of a perfect correlation and no correlation, right? So it'd be somewhere in the middle there. Yes, it only goes between 1 and negative 1. It will never go any larger or any smaller. 1 is the maximum, negative 1 is the minimum value there. Good question. Any other questions on R for right now? We'll look at a few examples and talk about it as well as we go on. Oh, I covered this up, but we will need it. Okay, I have too much stuff going on in this slide. I need to... Okay, so in Excel, we're going to use the function equals correl, and that's going to give you the R value, your linear correlation, so correl. Correlation abbreviated, basically that's what it is there. Okay, so correl. And then what you're going to do is inside those parentheses, you're going to select your first set of data, and then you'll put a comma, select your second set of data, and it will calculate the R value for you. You do not have to do it because the formula to calculate R is horrendous. You don't want to know what the formula is to calculate R because you will be sad. Just trust Excel. Excel's going to do it for you, you know. Okay. Excel is our friend. Exactly, Veronica. Exactly. So, like we talked about before, we're going to continue that idea of hypothesis testing, but what are we testing this week? Well, we're testing for correlation. We're testing to see if there's a linear correlation between these two variables. So, what's going to happen to determine our conclusion if there's a correlation is we're going to compare that R, that linear correlation, to our critical value. And I'll tell you how to find your critical value in a second. This ties back to last week. Remember when we were trying to find our test statistic and our critical value and compare it? It's similar, but it's actually easier this week. Yay! Maybe? Okay. So what you're going to do is you're going to take your R value, which you calculated using correl, the correl function in Excel, and you're going to compare it to your critical value. And your critical value is going to be found by going to page 692 in our textbook. This is the only time I will ever tell you to use your textbook. But there's a table in there we do need. It's called table A6, and we need it to interpret R. So if you haven't used your textbook and you're not quite sure how to get there, let me show you real quick. So you can just go to any module. I went to module 6. And then click on your e-resources and it will pop up here. And it won't be on this page, but what you can do is right down here in this tab here, you can just type 692 and it will take you right to this table. Did you guys find it? It's going to be your new best friend, this table. This table is going to give you the critical values for R. And the critical values of R, the first thing you'll notice is the first column represents your N value. Do you guys remember what N represents? What's the variable N represent? Anybody remember? You guys are probably still trying to find the page. Yes, sample size. Great. Wonderful. So that's the size of how many sets of data you're looking at. Pairs of data. Same thing as dependent samples we talked about last week. You're looking at the pairs. How many pairs do we have here? And the next column is going to say if your alpha is 0.05, meaning you're 95% sure, right? We're going to use that column to give us the critical value. So if my alpha is 0.05 and my N is 10, let's say my sample size is 10. What I'm going to do is I'm going to jot over here to find my critical value, which is 0.632, and that's what I would use for my critical value. I'm not calculating anything. I'm just simply grabbing the number from the table. That's it. And this last column would be if my alpha was 0.01. We would just go ahead and go over here and grab the number there. Okay, and that would be if I was 99% sure. And we'll use that for a second. And we can have two conclusions here. We can either have your absolute value of R, meaning we look at the positive value in R and we compare it with the critical value. If your R is greater than the critical value you found in the table, we're going to go ahead and reject the null hypothesis and conclude that it is a linear correlation. Okay. Rejecting the null hypothesis is good because it means there is sufficient evidence to support that these two variables have a linear correlation. Okay, you can create that straight line between the two. However, if your absolute value of R is less than or equal to your critical value, you have to fail to reject the null hypothesis and conclude that there is not sufficient evidence to support the claim of a linear correlation. Basically, it's not looking very linear. It's too spread out. So the data isn't straight enough to fit that line. It's not going to work. Okay, that's essentially what we're doing here. We're either trying to decide, ooh, does it fit that straight line, or no, does it not? Is the data too spread out? Note if alpha is not given, let's go ahead and default to 0.05. And I think we've done that for every single week, is where the default, if it's not given, is just 0.05. Just assume that. Okay. So we want to go ahead and take this table, and we're going to go ahead and find our correlation coefficient R. So let me go ahead and just pull up that Excel sheet that I handed out. It is on here. If you go to Sheet 2, the other tab, okay, so there's a Sheet 2 tab. All the information is up here. I believe I typed all of it in. Yep. And I'll zoom in so you can see this. So what we need to do is we need to calculate R. So I'm going to label it R, and I'm going to go equals Correl, and in parentheses, I'm going to select my first column, place a comma, select my second column, close parentheses, so I have both columns selected, hit enter, and we can see that our R, let me write this down, is 0.79494. Okay, so if we think about how close that is to 1, it's fairly close, right? You would say, oh, that's pretty close to 1, which is a perfect straight line, right? So we would assume maybe there was a linear correlation, but we have to be careful here because before we can make assumptions, we have to compare that to the critical value. And the critical value depends on how many samples we have. So here, what's our N value? What is our N value? What's our sample size here? What do you guys think? Remember, it's pairs of data. 5, very good, yes. So there's 1, 2, 3, 4, 5. So we'll have to keep that in mind when we're using the table. Now, let's pretend that we had more information than just this small little table, because I didn't want to type it all in. It's really me being lazy. But let's just pretend I added a bunch more information. Let's pretend I upped it to 23 pairs of data. So imagine I just upped it to 23 pairs of data. And I did that correlation coefficient again, and then I got R equals 0.801 for 23 pairs of data, rather than just my 5 pairs I calculated before. Okay, so I got more pairs of data, and I found that, wow, my R has actually improved. It's actually grown to 0.801. Yay, that's pretty good because it's pretty close to 1, right? It's fairly close to that linear representation. So is there sufficient evidence to support that there's a linear correlation between chocolate consumption and numbers of Nobel laureates? So what we're trying to do is we're trying to test the hypothesis now. So we're going to compare our R to our critical value. Now, how do we find our critical value? Well, we have to use that table from our book. So let's go over to our book real quick. Now our N was 23. Remember, I upped it. So now it's 23 pairs of data instead of the 5 that we practiced on. So 23, okay. So notice you have 20 and 25. Just pick the number that it's closest to. It's closest to 25, so let's use this row. Now we have to use this first number because that number represents a significance level of 0.05. So our critical value is going to be, let me move my pen here, 0.396. 0.396. .396. Now remember, to determine whether there's a linear correlation or not, you have to look at the absolute value of R and compare it to your critical value. So the absolute value of R is going to be 0.801. If that was a negative R value, we would flip it to a positive. That absolute value just turns everything to a positive. And our critical value is 0.396. Now, which number is larger here, our R or our critical value? Which number is larger? Our R is going to be larger, so we're going to throw a greater than symbol there. So I'm going to go back to my slide where I had my conclusion. Nope, that was not it. Okay. And I'm going to notice we're in this situation where my R is greater, right, than my critical value. That's what you guys told me. That means I should reject my null hypothesis exactly and conclude that there is sufficient evidence to support the claim of a linear correlation. So we would say there's enough evidence to support that there's a linear correlation. So reject the null hypothesis. And the null hypothesis says there's no linear correlation. So we would conclude basically there's sufficient evidence that there is a linear correlation. Now, just so you know, I abbreviated that because I didn't want to write it all out. I do encourage you to write that whole statement out just as practice, because they will expect you to write out that whole statement in your homework. Okay, now let's take a moment to step back and really analyze what this says versus how it applies to reality. So there says there is a linear correlation between these two variables of eating chocolate and becoming a Nobel laureate. Now, common sense tells you if I eat more chocolate, I'm pretty sure it's not going to make me a Nobel laureate winner, right? I'm pretty sure that they don't really have much of a relationship in the real world. Well, that leads into our next topic, which is correlation does not imply causality. And this is a thing that a lot of people struggle with. If you're ever on Facebook and stuff, they like to talk about this idea. People will share graphs and show a relationship between these two variables. They're like, oh, as this increased, this also increased. It must be a cause and effect type of thing, hence causality. But that's not always the case. You can have things that are correlated and match up to a nice linear relationship, such as global average temperatures versus number of pirates. Yes, there is a correlation between these two, but I'm pretty sure you're going to say, just because our pirates decreased does not mean that has caused our global temperature to go up, right? Okay, so here comes a little common sense into play, right? Another one is there is a correlation between the number of people who drowned by falling into a pool and the films Nicolas Cage appeared in. It's a really weird correlation. So these are just weird things that pop up that people are like, look at how they're correlated, but clearly they have no causality of one another, right? And that is actually what I did in the course announcements. I don't know if, did you guys see the course announcements? Let me see if I can pull it up real quick. Yeah. Hopefully it gave you a little chuckle, Lori. But correlation does not cause causality. And you can see here, sales increased and mustache length also increased. I'm pretty sure if you're a business person and you say, oh, if we increase all of our mustache length, I'm pretty sure the sales are not going to increase. Those two are not related to one another. And there's some other funny correlations here. If you want to just check it out, click on it. Explore, have fun. I think they're amusing. Obviously, there's not a causality there, so you got to be careful with that. And that's what happens a lot on Facebook, is it gets misinterpreted. So be very, very cautious with that, please. I'm just trying to do my civic duty, because Facebook just causes so many issues. Not gonna lie. Okay. Yeah. Okay, so now that we've decided how to determine if there is a linear correlation between two variables, how do we come up with that line that represents that relationship? How are we going to come up with what we call a regression line? What is that line? How do we come up with the equation for it? So this is where we're going to get into like a little bit of algebra, but promise you it's not too much. Okay, all math is interrelated somehow. It just is what it is. So the regression line can also be called the line of best fit or the least squares line. And it's basically the line that best fits the data. That's how we come up with it. So the regression equation is given by y hat, that little y with what looks like a little party hat is called y hat, equals b naught plus b1 times x. Now, quick note, y is your dependent variable, so y would be your vertical line, in case you need a little reminder from algebra. X is going to be your independent variable, X is your independent variable that will be on your horizontal axis. B naught is going to be your y-intercept. If you think of data and you're thinking of your y-intercept, think of it where it crosses the y-axis, or you could also think of it as your starting point, because usually we start when x is 0. So we start there and either you go up or you go down. Where's that starting point? That's going to be your y-intercept. B1 is going to be our slope. Okay, B1 is going to be our slope. So the cool thing here is we don't need to like graph this and then pick out the slope and the y-intercept from the graph. Instead, we have Excel. Yay! It does it for us. So in Excel, to find B1, our slope, we can use equals slope. Now, be careful here. Caution. When you are selecting your data in those parentheses, you have to select the y's first and the x's second. So the y's are your second column, and your x's are your first column. This is the only thing that I think really throws people off, is for slope and for intercept, you have to do your y's first and then your x's second. So your y's are your second column, your x's are your first. Otherwise, that will get messed up. We'll go through some examples so you can see how that works. It applies for your intercept as well. Okay, so once you come up with your regression equation, we can use it to predict future values. It's a prediction tool, okay? They use this in business a lot when they're trying to predict sales or how something's going to do or what's projected profit or whatever you want to look at when you're in business. Clearly, I need to take some more business classes. That's what that says. But the idea is you use linear equations to predict things, okay? Whether it's the weather or the number of chocolate chip cookies you're going to sell. I don't know. But the idea is regression equations are all around us. They get used in everyday life to help predict things. Now, when you're creating regression equations, we should consider the following. If it is a bad model, a good model, and correlation factor. So let's start with bad model. It is possible to have a regression equation which is a bad model, meaning that it's not very accurate at predicting things, such as maybe weather or where a hurricane is going to hit, things like that. You see a lot of science models here. But basically, if the regression equation does not appear to be useful for making predictions, don't use that regression equation. For bad models, where your R fails that hypothesis test, the best predicted value of a variable is simply its sample mean. And we'll get into an example of that. But basically what it's saying here is if you had to, if you tested your R against your critical value and it came back and it says, ooh, it's not a linear equation, ooh, then you would say, well, I can't really use that model. That's a bad model, meaning that instead what I'm going to do is I'm just going to take the mean of my y's and I'm going to use that instead. Now, if we got this linear equation, we've created this linear equation and we find out it passes that hypothesis and it is a linear equation, we're going to conclude that it's a good model. Yay! And we can use that model to predict things. We just need to replace my variable x with whatever number we're trying to predict and then simplify to calculate that value. Use the regression equation for predictions only if the linear correlation coefficient R passes that test, meaning that indicates that it's a linear correlation. And this only happens, so it's a good model if, I lost my pen here. It's a good model if R is greater than your critical value, meaning it's a linear correlation. It is a bad model if your R is less than or equal to your critical value. Okay. Meaning it's not large enough to represent a line. Okay. So here's some examples of R. So let's say R squared is 0.81. Notice here that this line, the data is pretty close to that linear regression line. Notice how the data is pretty clustered close to it. It looks like it's kind of feeding on the line. It wants to get closer. And that's because notice that number is close to 1. If you remember that scale, that means it's close to 1, meaning that it's closer to being that perfect linear equation. Okay, but look at the graph to the right. To the right, you'll see R squared is 0.24. Notice that number is closer to 0, right? When you're thinking of the number line here, here's 1, here's 0, here's -1. It's closer to 0, meaning that notice how the data is more spread out. Everything's kind of pushed apart. And it's not really fitting that line. It's not really too close to that line. And that means it's not really a great linear representation. We wouldn't say the data really fits that line very well, in other words. That's essentially what we're saying there. So it probably would not be a good idea to use that linear equation to predict things. You're most likely not going to get an accurate answer using that. So I just wanted to reiterate what we talked about. This is the same thing I just talked about, but just more streamlined. This comes from your book. So basically, you're asked to predict values of y, okay? Come up with predictions. So the first thing you have to ask yourself is this regression equation a good model? Is it? Question mark. How do we determine that? Well, we have to calculate our R value, figure out what our critical value is, and then compare the two. And use that comparison to determine, is it linear or is it not? If R is good and it is linear, in other words, our absolute value of R is greater than our critical value, we would say yes, that equation is going to be a good model. And we could go ahead and plug values in for X to predict Y. Just replace X in that equation to get Y. Now, let's say we test our R against our critical value and it comes back and it doesn't pass. In other words, the absolute value of R is less than, that should be less than or equal to our critical value. That means we did not reject the null hypothesis, meaning that there's not sufficient evidence to support a linear correlation. It's not looking very linear. That's like that example of the R squared was 0.23. It was all spread out. All the data is around. So no, the regression equation is not a good model. When it's not a good model, we're going to go ahead and use Y bar. Now, we have not talked about Y bar before. Y bar is the sample mean of the Y values. So remember you did X bar before where you just took the average of all the X's? It's the same thing. The only thing that has changed is now you're just going to look at the Y values. So you're still using that function average that we used to calculate our sample mean for X, but now we're just going to do it for the Y's. And remember, the Y's are the second column there. Okay. Let's go through an example to kind of walk through this, and then tomorrow I will do a few more examples. And again, tomorrow we will talk about deliverable 7. Yes, we are all very excited. Okay, so find the predicted Nobel laureate rate for Japan, which was 79.9 internet users per 100 people. Okay, so let's just look at this. It gave us a table of 1, 2, 3, 4, 5, 6 pieces of information. 2 variables are happening here, internet users and then Nobel laureates. So they're comparing internet users versus Nobel laureates. If there's more internet users, does that increase the Nobel laureates? Let's see. It's the same idea as chocolate here, people. There's really not going to be causation, but we can see if there's a correlation. So be careful between those two. Causality and correlation are 2 different things. Dun, dun, dun. Okay. So on here, we do have a third sheet. So just click on that third tab over there, and then just zoom in. The first thing that I want to do so that I visually see what's happening here is let's go ahead and make a scatter plot. I like to do this just to see for myself if I believe there's a linear relationship between these points, and I'm just not sure. So remember, you just click and select all of your information, go to your Insert tab, and scroll on over here to the scatter plot. Boom! Scatter plotted up. Oh, that looks beautiful. Now, you may say, well, it doesn't. It kind of looks like they're close. If maybe you drew a line here, it's a little iffy, right? Whether it's linear or not. So why don't we go ahead and put that off to the side for right now. Oh, I just dropped it down to the bottom, and we'll revisit that to really examine it a little bit more later. Okay. So let's go ahead and go through the steps to come up with our hypothesis test, come up with our equation, and see if we can predict things such as predicting when my X is 79.1. That's what they're asking for. Predict if my internet users are 79.1, how many Nobel laureates am I going to get? That's what they want us to predict here. So the first thing we need to do is our hypothesis test. So step 1, hypothesis test for correlation. I'm just going to type up the steps in Excel because it's just going to be easier than flipping back and forth. So the first thing we need to do is come up with our linear coefficient, correlation coefficient. That's a lot to say, it's a mouthful. So that's equal Corel. Now in Corel, you're going to go ahead and select your first column of information, comma, my second column of information, close parenthesis, hit enter. It looks like my correlation coefficient is 0.79912. Is that what you guys got when you entered it? Yes? Okay, perfect. Okay, so the next step is to find our critical value. We need to find our critical value here. Now, our critical value is based off of our n and our level of significance. So the first thing, we have to come up with our n, which is our sample size. Remember, it's just the pairs of data. And you are correct, Lori. It's 1, 2, 3, 4, 5, 6. Yep, Veronica and Lori have it. It is 6 for our n. So we're going to use that information. We're also going to say that alpha is 0.05. Boom. So let's go ahead and grab our book. That is not our book. There's our book. Now remember, the second column there is for alpha equals 0.05, so that's the column we're going to use. And we need to use n equals 6. So exactly, we're going to scroll over. It looks like our critical value is 0.811. Let's grab that and write it in there. 0.811. Okay. So we have our R and we have our CV. Which one is larger? Our R, so our absolute value of R and CV. CV is larger, our CV is greater. So we would say that, actually let me delete that. Our R is less than our CV. The R value is smaller than our CV value, you would say, which means that we can conclude we do not reject the null hypothesis. So I'm just going to label that HO. Yep, we fail to reject that null hypothesis exactly. Not sufficient evidence to support linear correlation. This is so much easier to type up. Not going to lie to you guys. A lot less time there than me trying to handwrite it out. So this basically means that it failed that linear test. It's not very linear. And if we go back down to our graph, you guys can kind of agree, it doesn't really seem like these lines, these points are really fit in a straight line there. So step 2, let me underline this. I want to underline it. Yeah. Did that work? Yay! Okay. Step 2. We still need to come up with that regression equation. Create regression equation. Make sure you spell equation correctly. That can cause problems. I like to just underline mine so that I know. Okay. So the first thing that we need to find is B0, which is our intercept. If you need to, you can write in there, oh, that's my intercept, my y-intercept. So to find it equals intercept. Now, remember, this is the one where I told you guys, be careful because look at what they tell you to insert. Your y's have to come first and your x's have to come second. So make sure you're selecting your second column first and then your first column second. So be careful of that. Make a note. Okay. enter. So it looks like the y-intercept is at negative 8.44. Do you have a different version of Excel? Are you working with 2010? Whatever your Excel tells you to do, just do whatever Excel tells you to do. If it says do X's first, go ahead and do X's first. If it says Y second, do Y second. As long as you get the same thing as me. That's why it's always good to practice this while we're doing it to make sure that your Excel is not different, because if you have 2010 and before, it can mess up a little bit, like it has slightly different functions. So yeah, sure. You said F11, right? Okay. Okay. So, boop, oops, nope. There we go. So for slope, we're going to type in slope. And my Excel tells me to do my Y's first. So I'm going to select my second column first and comma my X's next. X's are the first column. Okay, so it looks like we have a slope of 0.202798. Now, remember my function is y hat equals b naught plus b1 times x. And you're like, how do I type that in? So I'm going to give you the basic function and then we can look at it together. So we're going to have to insert a symbol here. So let's go over to insert, and then we'll go to symbols. So insert all the way to the end, we'll have to insert a symbol. Now, if you go to font, I don't know how to pronounce that. Slafan? Whoa. Go away, buddy. Thank you. Slafan, and make sure it's Latin extended. If you just scroll down, you should be able to find Y hat there. There's Y hat. But you have to make sure the font is Slafan. And once you use it once, it'll be in there in your recently used symbols, and then life's pretty easy. You just have to find it first. So grab that, hit insert, hit close, and then equals b naught plus b1 times x. Let's go ahead and just copy that. Now you need to replace b naught with your intercept, so that's going to become negative 8.44304. And your b1 is going to be your slope, 0.202798. And that is what your equation should look like. Now notice we're not doing any calculations when we're coming up with the equation. I simply want the format with your x and your y hat still in there. We are not replacing those. We're going to keep those in there because those are our variables. Those are the things that are going to be changing depending on what we put into this function. Okay? Any questions on how to come up with that? Now, we're going to go ahead and move on over here for step 3. I want to say no, but let me see. No, it's not going to let you, because you're not in the equals format, so it won't let you do that. If you want to calculate values, we'll be able to, but to write the equation, that won't work. Sorry. I know that's a bummer. Okay, so step 3 is predicting things. Hey now. Predicting. I'm really not going to write things. Or predictions, that would be better. Okay. So here, what does our problem want us to do? It wants us to predict the Nobel laureate rate, which is our Y value, our second row here, for Japan, which has a 79.1 internet users per 100. So that's its X value. If its X value is 79.1, what is its Y value? So let's go ahead and go back here. And it wants us to predict when X equals 79.1. So before we can predict that, we have to state whether this is a good model or a bad model. Now, what do you guys think? Do you think this is a good model or a bad model based on our hypothesis test? Good models mean that it's a linear equation, we're happy. Bad models mean that it is not a linear equation and we're not happy with it. What do you guys think? Good model or bad? So it would be a bad model because it failed. I shouldn't say it failed because that can be confusing. Basically, it's not a linear correlation, right? There's not sufficient evidence to support linear correlation. So that means that this is a bad model. So we cannot use it. Sad face. Okay. Let me scroll over so you can actually see what I wrote here. So we cannot use it, sad face. So instead, when it's a bad model, we need to use Y bar. We need to use Y bar for predictions. And Y bar is actually the easiest thing to use. Just hit equals and then go over and type in average and make sure you're selecting the average of your Y values. Your Y values are your second column here, so we're just going to select our second column, close our parentheses, and we find that Y bar average is 5.0667. So that would mean that our prediction for the number of laureates, Nobel laureates, oh my gosh, I am not going to spell this correctly, to be honest with you guys. Laureates for Japan should be 5.07. Looks like we're rounding to one decimal place, so let's round that to 5.1. So the idea here is if it's a bad model, we're going to go ahead and just use the mean of the Y's. And that will be our prediction for any number that you want, because our equation isn't a good representation, so we can't use it. Now, tomorrow I'll try to pick an example where it is a good model and we can see the difference then. Any questions on this one? Anything you want me to clarify there? Let me write that down. Step 3, predictions. Okay, so let's jump into our homework assignment, look through it together. Our homework assignment is a little bit different this week. So here's deliverable 6. This week, we're going to determine and interpret the linear correlation coefficient and use linear regression to find a best fit line for a scatter plot of the data and make predictions. So according to the U.S. Geological Survey, the probability of a magnitude 6.7 or greater earthquake in the Greater Bay Area is 63%. About 2 out of 3. In the next 30 years, in April 2008, scientists and engineers released a new earthquake forecast. So they're using models to predict weather. We've seen that before. As a junior analyst, you are tasked to determine whether there is sufficient evidence to support the claim of a linear correlation between the magnitudes and depths of the earthquakes. So is there a linear correlation between the magnitudes and depths of the earthquakes? So this week we're actually going to do a PowerPoint instead of a Word document. So it's a little bit different. So basically you're given a spreadsheet. So you're going to download that spreadsheet and it's going to give you information and you'll do your calculations on the spreadsheet and you will turn in that spreadsheet as well along with your PowerPoint. Come on, Excel, you can do it. I updated to 2016 and I think my Excel doesn't like me, which is not a good thing. Okay, so you will have that information. Hopefully it pops up in a second. And you'll have the two variables. The first one will be magnitude, the second will be depth, and you have to compare them. So on your PowerPoint, they break down all of the slides that you're going to include. There's 8 slides. Slide 1 is your title slide. Slide 2, introduce your scenario and data set, including the variable provided. The variables, excuse me, I already told you the 2 variables. But just talk about them. Slide 3, construct a scatter plot of the 2 variables. So just like you did before, include a description of what you see in the scatter plot. Ignore that business, should not be there. The only thing that added on that we haven't talked about is just include a description of what you see. What is going on in there? Does it look linear? Is the data really spread out? How are the variables relating to one another? Okay. Slide 4, find the value of the linear correlation coefficient R. So tell me what R is and find the critical value of R using alpha. That should say alpha equals 0.05. I have no idea what that is, but that should say alpha equals 0.05. And you can just ignore that too. They throw in random symbols here. I don't think it translates from Word documents very well. Include an explanation on how you found those values. Just a short, brief explanation, what you typed into Excel basically. Slide 5, determine whether there is sufficient evidence to support the claim of a linear correlation. So you're just comparing the R and the critical value here. Explain. Slide 6, find the regression equation. So you're going to be coming up with your, here's the data for Excel. You'll see there's 2 variables, right? Your X and your Y. Magnitude is your X, depth is your Y. And then those are the 2 columns. So there's quite a bit of data there, all the way down to row 51. So there's 50 pieces of data there to analyze. Let's see. So slide 6, you'll be given the regression equation. Y hat equals blah, blah, blah. Let the predictor X variable be the magnitude. Identify the slope and the y-intercept within your regression equation. That goes along with coming up with your equation, right? Slide 7 is the equation a good model or a bad one. Basically, that's what your question is. How do you know? And what would be the best predicted depth of an earthquake with a magnitude of 2? So that when they're asking you to predict things, do we use the regression equation or do we use Y bar? How do you know? That's the question they're asking. And then slide 8, conclude by recapping your ideas by summarizing the information presented in context of the scenario. So something a little fun, a little different, just do a PowerPoint instead of the regular. Deliverable 7 will be a PowerPoint as well. Questions on this deliverable? Anything you want to clarify? Again, I'll do a couple examples tomorrow in the live lecture at 5:30, and then move on. Feeling good? Hopefully. Because that is all I have for today. Yay! And then Friday at 1 will be open office hours as well. And then, okay, sweet. I find that a lot of people like this week a little bit better, especially when we do a couple more examples tomorrow. It helps just clean up any confusion that you may have had. Okay, well, thank you guys so much for coming tonight. I'm so glad to have you here. Yeah. Next week, I haven't hammered out exactly what I'm going to be doing. I'm debating between like a review to kind of get us ready for Deliverable 7 if anybody wants to go back and review, or just having open office hours. I'm debating between the two. If you feel strongly one way or the other, let me know. I'm going to think about it this weekend, and I will definitely post it on Sunday to let you guys know for sure what I decided. Yeah, after another example too. Good, good, good. Yeah, I know some people are starting new classes, so yeah, they may not. They may not want to come and they want to finish up, which I totally get. I totally understand. Okay, guys, if there's anything else that pops up or any questions on the homework, you know, you can email me or just come to the open office hours on Friday. Bye, guys. Have a wonderful night. Good night.